So for this one, we're going to take the derivative. And I just noticed that's a regular polynomial, so we can just use the power rule there. So I'll have 3 times 4 is 12x cubed minus 2x plus 11. Okay, and for the next one, I'm going to go ahead and rewrite the function y. I'm not taking the derivative yet. I'm just rewriting it so that I can see it a little bit better. 5x to the negative 5. Okay, now I'm ready to take the derivative. So dy dx. And again, since these are just powers of x, I can use the power rule. The derivative of x is 1. 5 times negative 5, or negative 5 times negative 5 is positive 25. X to the, and when I subtract 1 from that, I get negative 6. Okay, and the next one, I notice that this g of x is the product of two functions. I have this function, and I have this function. So since my function I'm trying to take the derivative of is a product, I'm going to need to use the product rule. And so I think the first thing I might do is rewrite g of x, because that square root I want to write as a power. So I'll rewrite g of x as e to the x times x to the 1/2. So again, I'll just kind of color code this. So when I do g prime, I want to do, I want to make that yellow. So I want to do So we'll do the derivative of the first function. What's the derivative of e to the x? That's just e to the x. Times, leave the second one alone. Plus, then I'm going to leave the first function alone, e to the x. And then the derivative of the second, so it's 1/2 x to the negative 1/2. And the very last one, I'll notice that my function that I'm trying to take the derivative of is a quotient. So it has this kind of top and bottom. And so when I find that dy dx, the way I remember this is low d high minus high d low, square the bottom, and off you go. So for the quotient rule, I can go ahead and do the bottom part squared. That's the easy part. X plus 9 squared. And then on the top, I need to do something that looks like this. Oh, it's a minus. Wait, it's a minus. So since I have a minus there, it actually does matter which order I do this in. So we'll do low, which is x plus 9, derivative of the top, so 8, x to the 7th, minus high, so we'll do the top function, x to the 8th, derivative of the bottom, which is just 1, and then square the bottom. And I would stop there. Don't simplify, because if you simplify, you might make a mistake, and also it's easier to grade if it's kind of still in this form. But I would recommend putting those parentheses in before you start dropping in all the pieces, because that way, since we have something like x plus 9, it definitely does have to have parentheses around it. So if you have parentheses around everything, then you won't forget to have parentheses. Okay, so part A, for number 7, I'm given a graph, and then I have this question. Determine a single numerical value for the constant a that makes the following inequality true. Okay, so this part looks like an average rate of change of f. This is like an average rate of change or some slope of a secant line. And then this side over here is the slope of a tangent line, or an instantaneous rate of change. And at x equal 2, so when I go over here to x equal 2 and go up, I can see that the slope of the tangent line is 0. So really what I want is I need to find a value for a such that f of 2 minus f of a over 2 minus a is less than 0. So I need that secant line to have a negative slope. So if I'm looking over here at my function, I want my secant line to go through this point, And then I need to find another point that makes a negative slope. Well, if I go this way, I'll have a positive slope, so I don't want to do that. So to get a negative slope, I need to go this way. So really, any of these y values kind of to the right of 2 would work. So I'm just going to pick 4. But I could have done 3, or I could have done 4, or 5, or 6, or even 7. I mean, a lot of those are going to give me a negative slope of that secant line. So there are really a lot of answers. You could have put 3.5, I guess. So there are different answers that you could get for A, but it just needs to make a negative slope with that secant line. Okay, let's look at the next one. Determine a single numerical value for the constant b that makes the following inequality true. Okay, so on this one, I need to have some sort of, this is again a slope of a secant line. But this needs to go from x equal b to x equal b plus 0.5. Okay, so in some interval of 0.5, I need to have, it needs to be a negative slope, but not less than -1. So, so maybe if I go like, okay, so I need it to be a negative slope. So maybe like 2 to 2.5. That's an example of a slope. And is that slope, it's negative for sure, but it's not very steep. So that slope is going to be, let's see, the rise is like -0.2, and the run is 0.5. And so that's going to be less than negative, or that's going to be greater than -1. -0.2 over 0.5. So that's -0.4 is that slope. So that's between -1 and 0. So if we did b equal 2, that would work. Now, that's not the only answer. It might be like maybe 7 to 7.5 might be less than -1. But from then on, it gets too steep for this part of the graph for past beyond 7. But you might be able to do like 2.5 to 3. That might give you a slope less than that's negative, but not less than -1. But that's greater than -1. Okay, so the next one, find a single numerical value for the constant c that makes the following equality true. So again, this is the derivative, definition of derivative, and we want that derivative to equal 0. So really we have two options here. X equal 2 would work because that has a slope of 0, and x equals 7 would work. So either of those. So just pick one. So I'm just going to say 7 because I haven't used that one yet. So at x equals 7, we have a 0 slope. You could have also put x equal, or c equal 2. All right, so for this one, I have a lot of different things here. So let's see, how do I want to look at this? Well, let's start with A, and we're going to find all the pictures for which that limit exists. Okay. So for the limit to exist, the two-sided limit, we need the right and left-hand limits to be the same. So for this jump discontinuity, that does not exist. For this one, the removable discontinuity, the left and right-hand limits are the same, so this A works here. For the vertical asymptote, the limit does not exist. For the continuous, the limit does exist. And the horizontal asymptote, the limit at A does exist, so there. All right. What about the next one? For B, I need to find f of A exists. Okay, so at A, the function is defined, so B works here. For this one, there's a hole at A, so B does not work there. For this one, there's an asymptote, and it's not defined at A, so there's no B there. How about here? It's defined at A, yep. So B is true there. And for this one, f of a is defined there. So put a b there. All right, what about c? The limit exists, but the limit is not equal to the value. Okay, so c is not true because we already said the limit doesn't exist. So for here, the limit exists but does not equal that value. So I'll put that here because f of a is not even defined. So down here, the limit exists but it is equal to that value. And here the limit exists but it is equal to that value. So c is the only one that on that removable discontinuity. Okay, how about this one? The left and right hand limits are not the same. So that is true at this jump discontinuity. This one, the left and right hand are the same. At the vertical asymptote, the left and right hand are not the same. And that's the only one. Okay, the next one. The limit is equal to that. So that will only be true when it's continuous at A. So that'll be here and here. Okay, back up to this one. Okay, so here it says the limit as x approaches positive infinity exists as a number. Okay, so let's see what we could do here. So for this jump discontinuity, as x goes to infinity, it looks like this is going off to infinity. So I'm going to say no there. Here, as x goes to infinity, that looks like it's going to down to negative infinity. Here, as x goes to infinity, that looks again like it's going down. Here, as x goes to infinity, the function's going up, and here, as x goes to infinity, the function's going down. So it looks like none of those, f doesn't work for any of them. Okay, what about this one? The limit as x approaches negative infinity exists as a number. Okay, so let's go the other way. So as x goes to negative infinity, that one's just going down. As x goes to negative infinity, that one's going up. As x goes to negative infinity, that one's going down. As x goes to negative infinity, that one's going down. For this one, as x goes to negative infinity, that one's approaching some specific number. So I'm going to say G on this one, but none of the others. All right. And here, it says the limit as x approaches A from the left is infinity. Okay, so let's see here. So the limit as x approaches A from the left, this one is some specific number. As x approaches A from the left, that's a specific number. As x approaches A from the left, we get infinity. So this is at H. Here, as x approaches A from the left, we get some number. As x approaches A from the left, we get some number. So that's the only one. And then this one says the two-sided limit as x approaches A is infinite. So that means the left and right hand limits both have to be approaching positive infinity. Now the only one that was even close to approaching infinity was this one, but when I come in from the right, it goes to negative infinity. So I doesn't actually work for any of them. So I think that's it.